Hello, everyone. We are going to start talking about gravitation and the very basics of astronomy today, so stay tuned for that. Gravitation, we have very close, very close to the center of, or to the surface of the Earth. We have the law that F gravity is equal to mg, but this isn't the entire truth. This isn't the truth as we go out into different systems, as we go farther out from gravity, as we go farther out from the center of the Earth, as we go to different planets or around the sun, or change our radius or the mass of what we're orbiting, or anything like that. So this is only true for the surface of the Earth, when in general what is true is that Fg is equal to G times mass of two uh the mass of one object times the mass of the second object over the radius between the two objects squared, pointing in the direction from R1 to 2. So this is called F12 as well. It's the force of 1 on 2. And then this is the direction pointing uh from 1 to 2. So for example, if we have some mass here with a mass little m, and then it's going to be attracted to another mass with a mass big M. So the force is going to be pointing towards this radius, over this radius, in the direction of this radius, F12, and then the force of the other mass is going to be pointing F21 in the opposite direction towards this second mass, or towards the original mass that we were talking about. So F12 equals GMM over R12 squared in the direction of R12. So this is just going to, when we talk about FG equals mg, we get G m of the Earth times the mass of the object over the radius of the Earth squared, pointing towards the center of the Earth. So G is going to just be equal to G me over re squared. And because the mass of the Earth obviously isn't changing, and the radius of the Earth from the center of the Earth doesn't get much bigger or doesn't get much smaller as you climb Mount Everest or go to the bottom of the Mariana Trench, then this is going to be pretty close to constant no matter what. So hopefully that should be helpful to you. That is the fundamental thing that we're going to be learning here. Just this equation that F of force of gravity is equal to G times the mass of one object times the mass of the other object over the distance between the two objects squared, pointing towards the other object. Okay, so that's the main thing that you need to learn here. Uh, the other thing that we're going to talk to you about is just the ideal of circular motion or orbits or elliptical orbits. So we know that, oh, okay, I can make this bigger. We know that the Earth revolves in a circle, so there's going to be some sort of acceleration uh, where F centripetal is equal to m times a centripetal is going to be equal to force on a scale minus mg. So uh, what this means is that uh, we've done this type of problem before where somebody's on an elevator and this force on the scale is going to read different values based on where how fast you're accelerating. The difference being that this one, if you're on a scale here, then you have no centripetal acceleration. If you're on the scale on the North Pole, you have no centripetal acceleration. Because you're only moving around you're only spinning around and on the actual axis of the Earth. So none of you has any angular velocity. So v perp is equal to r times omega, where r is this angle between where r is again this angle between or this distance between the central axis and the scale that you're reading or the position you're at on the Earth. So r v perpendicular equals r slash omega. At top, v perp equals 0 times omega equals 0. So you're not going to have any change to the you're not going to have any change to the centripetal uh from your initial value, or you're not going to have any change anything that's going to be causing centripetal acceleration from your initial value. It's just going to be the normal force pulling you in. So the normal force, which is force of the spring, is going to be equal to mg in this case. So it's just going to be equal to uh, AC equals r omega squared equals 0 equals fs minus mg yields fs equals mg at the pole. And then this obviously isn't the case always, so m r squared mr omega squared is equal to negative mr omega squared is equal to s scale minus mg. which gives us F scale is equal to M times G minus R omega squared. And then this is going to be at its height. Difference at the highest difference for R goes to radius of the Earth at the equator. Okay. So that's the main things that you're going to learn about the actual force itself. Another thing that we want to point out is that instead of just having a constant G, like we were talking about earlier, we have G uh, if we draw it out where a mass is at the center, then you're going to have a bunch of different values for G, all pointing that get stronger towards the center. So that graph wasn't great, and all point towards the center. So this is going to be, instead of just one constant value for G, it's going to be a vector field for G. Where the arrows indicate which the magnitude and direction of G at any given time, or at any given position. And then let's see, what else do we have to do? Uh, so we've talked about force, now we can talk about energy. And then another thing that I probably should have done that I didn't explicitly tell you is that when you do that correction to the scale, when you look at the scale force versus the actual weight mg, the correction is something like 10% or 3.7 or 0.37, I think, percent. So it's like very small. So this is, yeah, it's 0.34% the value of mg at the highest point, at the most, at any given at any point on the equator, at the point on the equator where the change is maximized, it's going to be equal to about 3.34% of mg. So it's not like a terrible amount. So how about the potential energy of gravity? U equals negative F dot dr equals negative from R1 to R2 G M1 M2 over R squared dr, where again gravity or energy is always going to be seen as the difference between 2 points, instead of being some value that's always going to be Yeah, instead of some value that's always going to be uh it has a specific 0 point. You can, instead of that, you can choose your 0 point. So if we're talking about close to the surface where we have MGH as our gravity, we can choose where our H starts. Does it start at the top of a clock tower? Does it start at the ground? Whatever you want to do. In this case, it's integrated from R1 to R2, which is going to give us negative, positive G M1 M2 over R, from R1 to R2. Oh, negative, and then it's also negative to positive up here. So this is just going to give us negative eventually. So this gives us negative G M1 M2 times 1 over R 2 minus 1 over R1. And if we choose R1 to be equal to infinity, this goes to negative G M1 M2 over R 2, which is just going to be equal to negative G M1 M2 over R, where R is the distance between uh your is the distance out from your initial position, or the distance you are out from uh the initial mass causing there to be a gravitational change. So this is important, and the total energy E is equal to 1/2 mv squared minus gm m over r1, or just r. So for a circular orbit, v is equal to square root, or v squared over r, v squared over r is equal to g m over r squared. So v squared equals g m over r. So 1/2 mv squared, E equals 1/2 mv squared, is minus g m over r, is going to give you equal to 1/2 g m over r minus g m over r is equal to g m over 2r for circular orbits, and then, or negative g m over 2r for circular orbits. So the important thing to note here is that this u never gets bigger than 0. So if uh total energy is less than 0, is it is in a uh stable orbit. So in this case, for circular orbits, they are stable orbits. They're not going to collapse into each other. They're not going to go off into infinity. They're just going to keep going around in a circle forever and ever because E is never going to be bigger than the potential energy no matter where you get in R. So as E is less than zero, or it might collapse into each other if you like add a little bit of energy and like press it going down towards the sun, then uh it is possible for the Earth is a pretty stable circular orbit. It's only comes off from circular orbit about 2%. So if you as long as you maintain this circular orbit, then you're never going to collapse into the sun because you're always going to be as far away from the sun as you are at any given time. And then the last thing that I want to do for classical, or no, not even classical, because we're going to do something about Kepler's laws, which is even before uh the everything we've been coming up with now. I think everything we've been doing right now has been Newton. Uh, has been Newton. So Kepler was before that, and that's who Newton based this observations on. But first, we have the escape velocity. So E is equal to K plus U. And what we want is some velocity where at the end it's equal to one half. It has exactly enough energy to go one half m0 squared plus uh minus g m m over r squared and uh at radius of infinity. So we want to know what distance out you have to go, or what speed you have to pick up to be able to go infinitely far out to completely escape and have zero velocity as you go infinitely far out, but uh just barely being able to go as far out as like you can go far out. So basically what this means is that velocity at speed at r equals infinity and is going to be zero, and that means because r is equal to infinity, so is the potential energy. So k plus u equals zero. So one half m v escape squared plus minus g m m over r squared equals zero. V escape squared is equal to g m times 2 over r squared. So V escape is equal to square root of 2 g m over r squared. Oh, I'm stupid. Yeah, this wasn't looking right, and the reason it wasn't looking right is because it's over R, not infinity. It's over R, not R squared. So this is just G 2GM over R. And then last thing to do is that uh if we're in a circular orbit again, then G M M, where M is whatever you're orbiting around, and then little m is doing the orbiting. Over R squared is equal to M a centripetal is equal to MV orbit squared over R. We found that V orbit is equal to square root of G M, the object doing the orbiting, over R. And then T is equal to 2 pi R over V, which is going to be equal to 2 pi square root of R squared. Excuse me. Over GM. So T squared is proportional to R cubed. And that is going to be our first introduction to Kepler's third law before we get into it next session. All right, so see you then.